So good morning, everyone. So we are continuing with module number 10, part 2, which is on interval estimation. And also we talked about estimator and also point estimate, right? So the short form for point estimator and point estimate, you can just call it as estimate or just estimator. So we talked about that yesterday. And what is it? Yes, I heard some noise. Anyone has any question? No question? Okay, I'm going to continue. All right, so we talked about estimation, and I gave you an introduction on hypothesis testing as well. And then I told you that theta represents point estimate, whereas the uppercase theta, given by this symbol, this is an uppercase theta, is your point estimator. The point estimator is basically the equation, whereas the point estimate is the numerical value. And then we also discussed about the examples of estimation that we have to do in our daily life as an engineer, maybe in the future. And then we also talked about biased and unbiased estimator and which one is the best and so on and so forth. And I gave you this definition. If an estimator is unbiased, therefore the estimator minus the point estimate is going to be equal to 0. If you overestimated or underestimated your parameter, therefore your bias will be greater or less than 0. It's not going to be equal to 0. So if it is equal to 0, then therefore it is going to be unbiased. So what is an example of unbiased estimator is we have two estimators over here, estimator number 1 and estimator number 2. And you can see that both of them have the same mean as the theta, which is the point estimate. Therefore, we can see that these two estimators are unbiased because they have the same center. They center around the same mean. Okay. And then we also talked about the most efficient estimator, which has the least variance. So if you were to compare between several unbiased estimator, they can have different variances. Therefore, the best one or the most efficient estimator that you would pick would be the one with the least variance. So first, you have to distinguish between biased and unbiased. You pick the unbiased, of course. And then when you have several unbiased estimators, you pick the one with the least variance. Okay. So your minimum variance unbiased estimator is known as MVUE. Okay, we also talked about that. Okay, so I'm going to continue with this one. So the standard error of an estimator is its standard deviation. The standard error of an estimator is its standard deviation. Previously, we talked about how the most efficient one and the biased versus non-biased. But now we're going to talk about the standard error. So there's a lot of things that we can describe our estimator by, right? Given by this guy equals to the square root of your variance of your estimator. If the standard error involves unknown parameters that can be estimated, substitution of those values into this guy produces an estimated standard error denoted by, okay, this is like a very lengthy definition. Wait, I need to check on my son. There's a weird sound. So what are you doing? Okay, sorry about that. False alarm. Okay, so I think everyone had a chance to read this, but it's very lengthy and doesn't really make much sense. So let's take a look at an example so that we can better understand what that statement means. So an article in the Journal of Heat Transfer described a new method of measuring the thermal conductivity. So basically, we just want to measure thermal conductivity, and they reported in this journal. When you become an academician or you become a lecturer or a researcher, you publish your findings in journals. So this is what they are doing. So we are referring to that journal that has been published because it is verified data. It has been performed experimentally and they record it and they publish it. And it's not easy to publish a journal because it has to go through a peer review, which means that several other people who are experts in that field will have to read your work and say and tell you what you did wrong in your work. So it's quite hard. I have a hard time publishing as well, but it's a nice feeling when you manage to publish. Describe a new method of measuring the thermal conductivity of Armco iron. The following 10 measurements of thermal conductivity were obtained. So we have our 10 measurements. They have taken these measurements from the article. A point estimate of the mean thermal conductivity is the sample mean, or we can just calculate this normally. We just add all of these, the regular sample mean. And then the standard area of the sample mean is this one. We know this equation. Our standard mean would just be mu. And the standard deviation of our sample mean would be this equation. But since we don't know what our population standard deviation, therefore we can replace it with our sample standard deviation, which means that you can calculate your sample standard deviation just from this sample. Okay, so what does this have to do with the definition? Let's go back to the definition. Here, what we did just now was, instead of finding the actual value, we don't know what the value is because they didn't provide it to us. And they gave us a sample from an experiment. And because we don't have the actual standard deviation, we can substitute this for S. And this was based on the definition, whereby if the standard error involves unknown parameters, which is what we saw just now, that can be estimated, substitution of those values into the standard deviation produces an estimated standard error. So you can actually put in the value of your sample parameter instead to get the standard error. Doesn't really make sense, but this is how they verified it and it works. So we follow that. They are the experts. Okay, so because they use the S from this sample data to put inside the equation to find this guy, therefore the answer for, the standard deviation for this, or the standard deviation estimator, would be 0.0898. So this is our estimator. The standard error is about 0.2% of the sample mean. Let me write this. Estimator. This is what they're trying to do. They are trying to find the estimator and comparing it, trying to figure out if this estimator is good or not. The standard error is about 0.2% of the sample mean. How do we know this? There is 0.2% of the sample mean. So our sample mean is this guy, and this one divided by this one times with 100. Let me just double check on that. 898 divided by 41.924 times with 100. So you would get 0.214. 0.0898 divided by 41.924. You make this as a percentage, so you just times it with 100. So you would get 0.214%. Okay, so the standard error, which is this guy divided by the sample mean, is 0.2%, implying that we could have obtained a relatively precise point estimate of the thermal conductivity using this estimator. How did we get this estimator? We used our sample standard deviation. Okay, so it's like philosophy in a bit, which I'm not going to comment further on that. Okay, do we have to learn this? Yes, somehow. Even though we are engineers, we have to learn this. And somehow, sooner or later, we will have to apply it in our work. Trust me. Now it doesn't seem relevant, but in the future it will be. Okay, so with that said, that's the end of your estimator versus point estimate discussion. So now we're continuing with the third subtopic, which is our last subtopic, which is the confidence interval. Previously, I told you that there are two types of estimation. One is, let's go back to that one. One is point estimate. The other is interval estimate. So confidence interval is a type of interval estimate. Okay, so this is under the classical methods of estimation. Okay. Okay, suppose that we estimate the mean viscosity of a chemical product to be this guy, which is 1000. This is our mean, sample mean. But because of sampling variability, you need to say you have your population, you take a sample from here, sample number 1. Let's say sample number 1, the sample mean is 1001. Whoop, it's not 1001. 1001, maybe, I don't know. And then you take another sample from this population, sample number 2. I'm recording, right? Yes, sample number 2. And you get a different mean. You get your mean as 990. Is it incorrect? No, it's perfectly fine. This is what you got from the sample. So this is what it means by sampling variability. You can make a point estimate from your sample, but it doesn't really tell you how close it is to the actual true mean. Yes, this is your sample mean. This is your sample mean. It follows a normal distribution, which we discussed using the central limit theorem, but it doesn't tell you how close it should be. So this one is 1. Let's say your actual mean is 1000, right? This one is 1. It has the value of 1 from the mean, from the population mean, whereas this guy is 10 away from the mean. So is this within the right interval or not? So we have to determine what interval. We have to determine the interval so that we know that our estimation is correct or not. Basically, that is what it means. Okay, so the point estimate says nothing about how close is our estimator to the actual population mean. Is the process mean likely to be between 900 and 1100, or is it likely to be 990 to 1010? So this one is, you have 100 away from 1000, right? Positive, minus. But this one is 1000 plus 10 minus 10. So this one is more precise. This one is a bigger interval. But which one is more reliable and which one is more precise? So this is what we're going to discuss after this. So bounds that represent an interval. Bounds that represent an interval of plausible values for a parameter in an interval estimate is known as confidence interval. Okay, that's your introduction. Okay, so now we talk about, of course, the equations. So from the previous subtopic, we know that we have a sample mean, normally distributed. Oh, where's my pencil? Our sample mean, if we take a sample from this guy, we know that it centers towards the mean. It has a mean that centers at the, the center of the population, and it has a variance of standard deviation of the population divided by square root of the size of the sample. It follows this. So a confidence interval estimate for mu is an interval of the form mu less than u, bigger than L. So L is known as your lower confidence limit, and U is known as your upper confidence limit. Different samples will produce different values of L and U. Why? Let's see. In our previous example, I said I take 2 samples from this population that is normally distributed. Therefore, the sample is also normally distributed. And you got your mean as 1001 and 990, right? So if I were to say that my confidence interval for this sample is This is too early to introduce it. Okay, sorry. Let me rephrase that. How do I say this in a way that it won't confuse you? Okay, let me show you this graph first. So remember that our population follows a normal distribution in the example that I told you earlier. And this is the mean. Let's say your mean is 1,000, right? And the sample mean that you got is 1,001. If you say that your mean has a confidence interval of 95%, then your sample mean can be between these values. And if you were to drag this bar, if you were to drag your values around this horizontal bar, it would overlap the mu. It would overlap your population mean. So this tells you that your sample mean is reliable to predict or to estimate your sample mean. Okay, bear with me. I know it's quite a statement. Okay. Now let's talk about this one. Different samples will produce different values of L and U. So if I take another sample and I got it as 990, and I say that whatever sample that I get has a 95% confidence interval. So the same thing can happen here. I drag my bar across 95% confidence interval. I'll tell you more about this later. And it overlaps mu. So my estimation is reliable. But what if my sample, I take my sample, but the mean is outside the confidence interval? Okay, please bear with me. This is just your exposure first. Okay, so I take another sample. Now it is, let's say 1,200, quite far, right? 1,200, the mean that I get is 1,200. Now it is beyond the 95% confidence interval. How do I know that? Because if I make a bar that is 95% from this mean, using this mean as the reference, sample mean as the reference, if I drag it across the values that is plausible within this confidence interval, it does not overlap with the mu. So sometimes our sample value does not hit the target. So this is why we have our confidence interval. So let's say my confidence interval that I specified earlier is 95. 5% of the time, my sample mean would not hit the target. Okay, let's talk more about this. So this is an example, very lengthy, but hopefully we can make sense of it. A quality control engineer draws a simple random sample of 100 boxes. This is our N from the population of boxes that have been filled by that machine on that day. So our 100 is our sample size. It is from a population of boxes for the entire day. He computes that the sample mean will be sample mean of 12.05 mil and the sample standard deviation to be S equals to 0.1 mil. So this is our value that we have so far. Okay, S equals to 0.1 mil. We don't have to use the units here. Since the population mean will not be exactly equal to the sample mean because of sampling variability, we are not sure if it will be exactly the same as our population, but we know that it is normally distributed and it will center towards the mean. This is what we know. It is best to construct a confidence interval around 12.05 that is likely to cover the population mean. So this is what they are doing. So this is our sample mean that we got, 12.05. Our mean is unknown, but it centers in a normal distribution. So this is a 95 confidence interval. I'll tell you more on why it's 1.96 times with the standard deviation of the sample mean in a bit. Okay. Okay, since X is the mean of a large sample, our sample is 100 and it is greater than 30. Therefore, it follows the central limit theorem, which tells us that the sample must be normally distributed and whose mean is mu and whose standard deviation is this guy. When we talk about the normal distribution whose mean is mu and this, it doesn't mean that our sample mean is exactly mu, but the normal distribution from which we take our sample has this value. We take our sample, it can be anything. The sample can be away from the mu, the sample can be close to the mu, it can be exactly on the mu, but the sample will always follow this normal distribution, and the normal distribution centers towards mean mu. So this is what it means of the central limit theorem. Okay, so the population mean and variance is unknown to us, yes. The observed value sample mean 12.05 is a single draw from this distribution. Like I told you before, we can take many samples from the population and it will give us different values. How confident are we on this value that on the sample value that we have? How confident are we? So this is the function of confidence interval. Okay, so let's look at this figure now. So the sample mean is drawn from a normal distribution. From this particular sample, the sample mean comes from the middle of 95% of the distribution. So our mean, if we are specifying a 95% confidence interval, this will be 95% from the center of this normal distribution. And then our sample mean will also have a 95 confidence interval. So here, the 95% confidence interval sample mean plus minus 1.96 times with the standard deviation of the sample mean, of the sample succeeds in covering the population of mean mu. Okay, let me give you another example because, the first time is always not the best. So second scenario, another sample is drawn. So this is our sample number 2. But this time our sample mean that we get is outside the 95% of the curve. So it's here. Only 5% of the samples that could have drawn fall into this category. If we are going to sample from the population like 100 times, not 100 times, this is the same as the end. If we are going to sample from the population, what's a good number? 10 times. I am the engineer, I sample 10 times for that day. From this 10, this is not a good number as well, 0.05, sorry. 0.5 times this number, which is not a good number. Let me use a different number. The 20 times that the engineer sampled from this population, 0.5 of this, what would that be? 0.05 times 20 is 1 time of this sampling would fall outside of the confidence interval, whereas the 19 times that the engineer samples from this population, it will fall within this confidence interval, and the value would be within the confidence interval of mu, which is good. So 19 versus 1, pretty good. So the more samples that he does, the more sampling times that he does, let's say 1,000, the more that he will see that it is obvious that the values that he will get for the sample mean lies between the 95% confidence interval. So he will get a lot of sample means, right? He will get a lot of these values, and he will see that these values will center 95% within this range, and only 5% will be around this one. Okay, so 95% confidence interval fails to cover the population. Sorry, for these 5% samples, okay, the 95% confidence interval does not cover the population mean. So only for 5%, but the other 95%, it will cover. Okay, so let's go for another example. Any questions so far? I know you have a lot of questions, but everyone's just confused at this point. We'll do more examples, don't worry. Okay, so I'm going to continue if you don't have any questions. So this is your normal distribution. The sample mean is drawn from a normal distribution with mean mu and standard deviation of this guy. We know this. This is from our central limit theorem. The quantity z, which is our cumulative distribution function, right, is the z-score that cuts off an area of alpha over 2. Alpha over 2. I think I skipped on alpha. Yes, I did not tell you about alpha. So I told you that the mu is between lower confidence limit and upper confidence limit. And it has a probability, this mu between upper limit and lower limit has a probability of 1 minus alpha. 1 minus alpha is called the confidence coefficient. 1 minus alpha is the confidence coefficient. And if you multiply this with 100%, you would get the confidence interval. So alpha is going to be very important for this subtopic. Okay, let me repeat myself here. We have our mu as our unknown, and we want to specify our confidence interval, right? We specify a confidence interval as 95%. Let's say it can be any number, but I'm going to specify here it is 95%. So for 95%, I have to specify a value for my U and also for my L, or a range. And to specify this range, I need to know what is my alpha, which is 95%. So it gets a little bit confusing at this point. 95%, so I can solve for alpha. So alpha will be 5 or 0.05. And then from here, I can look at the CDF table. And from the CDF table, I can specify this value. We'll look at that later. But what we need to know here first is that 1 minus alpha is the confidence coefficient. 1 minus alpha times 100 is the level of confidence. Level of confidence. Okay, because our confidence is in percentage, right? So you multiply this with 100, you would get this percentage. Okay, and alpha must always be between 0 and 1 because it's a probability. Okay, so those are the definition, or like the terms. And then we talked about what if the sample mean is within the 95% confidence interval. Therefore, your sample mean would cover the population mean. And sometimes 5% of the time that he samples, the sample mean would fall outside of the 95% interval. So 5% of these samples, the 95% confidence interval will not cover the population mean mu. So sometimes it works, sometimes it does not. That's just how data is. Okay, so now we're moving on to this part. Now I can introduce you again to alpha. So here we have mu, and mu is within the range mu plus z alpha over 2 times with the sample standard deviation. And where this is the range. So it's plus minus actually. This is plus and this is minus. It is exactly the same value. So I can say plus mu plus minus z alpha over 2 standard deviation of the sample mean. Okay, so it's a plus minus. It is symmetrical. It follows a normal distribution. And this value is 1 minus alpha. It is probability, right? Okay. So if this is 1 minus alpha, that leaves me with the shaded region as alpha. So if they are symmetrical, I can divide this by 2. So you get alpha over 2, alpha over 2. So if I were to add all of this together, 1 minus alpha, I would get 1, which is the area under the curve. So this is just another way of seeing it. So 1 minus alpha, what you are left with is just alpha. And you divide it by 2 because it is symmetrical. And this one is what, alpha over 2, alpha over 2. Okay, so how do we determine this guy? This is the important part here. The quantity minus z alpha over 2 is the z-score that cuts off an area of alpha over 2 in the left-hand tail. And for this guy, it is for the right-hand tail. So I'm just going to go to the example so that we can better understand this. So you saw that earlier, the range was mu plus 1.96, blah, blah, blah. And I told you, don't worry about the 1.96. We can figure it out later. So this is how we can figure it out. They are just listing it out, but basically we will try to find out how to find these numbers using the cumulative distribution function table. But these are just like the general rule. You don't have to memorize it because you can always refer to the table later on. But a mean plus with 1.96 times with the standard deviation of the sample mean is 95% confidence interval for mu. So this is where we got the 1.96 times with this one. This is where we got it. And how do we find out how do we make sure this is correct, right? So okay, I'm going to tell you how to do that. So here we can see that 1 times with the standard deviation of the sample mean is 68%. 1.645 times with the standard deviation of the sample mean is 90%. You can memorize this, no problem. But if you don't want to memorize this, it's also fine. 1.96 is 95, 2.58 is 99, and also 3 is 99.7. So these are like values that you will typically see in the questions. You don't have to memorize it. So summary. Yes, question? No question? Okay. So let the random variables x1 up to xn have a large n greater than 30 from a population with mean mu and standard deviation so that your sample mean is approximately normal. Then a level 100% times with the confidence coefficient percent. Confidence interval for mu is this guy, plus minus, right? Your range. Where your standard deviation sample mean is this guy. We already know this from the central limit theorem. When the value of your standard deviation of population is unknown, it can be replaced with the sample standard deviation S. This is what we did earlier on for standard error as well, right? Same case over here. If you don't know what the value is, you use S. Okay, let's go for an example, an actual example that uses numbers. Okay, the sample mean and standard deviation for fill weights of 100 boxes, this is our N, 100 boxes, okay? Our sample mean is given 12.05. Okay, I want everyone to focus here. And S is 0.1. I know it's very philosophical, but we have to make sense of it. Find an 85% confidence interval. So 1 minus alpha would be 0.85 because they asked us to find an 85% confidence interval. Remember, I told you 1 minus alpha times with 100% is your confidence interval, which is 85%. So if you were to get rid of the percentage, you are left with the probability 1 minus alpha 0.85, or you are just left with the just call it probability. Okay, so I'm just going to keep it like this. This is just for your understanding. So what's the next step? This is our first step. Finding out what is the confidence interval that they want. This is step number 1. Step number 2 is, let's go back to the definition. We want to find our range, right? We want to find our confidence interval, and our confidence interval follows this. So I'm going to copy this, plus minus z alpha over 2 standard deviation. Okay, hoping I remember that. So x plus minus 2 sample mean plus minus 2 z alpha over 2 standard deviation of our sample mean. So if I were to expand this, I know that my alpha is, what is my alpha here? I did not solve it yet. My alpha is 0.15. Therefore, alpha over 2 could be just 0.15 divided by 2. So that is going to be a 0.075. First step. Second step, put in the numbers. Z 0.075, but let's just say 0.075, and your standard deviation of your sample mean would follow this one, n. So I don't know what my population mean is. What should I do here? What did I tell you? If I don't know my population mean, what should I substitute it with?
Standard deviation.
Right? So if I don't know this one, I can use S over square root of n. It will still give you the confidence interval. So here, S over square root of n is 0.1 divided by 100 square root of 100. So that's just a 10. Okay, so leave this guy first. Let's go for this one first. Z of 0.075. 0.075. Okay, so this is the value of your CDF. And we want to know what is the actual value of Z. This is the CDF. Okay, this is the CDF. I want to know what is the value of Z in the table. So if we are talking about positive 0.075, it means that I need to know 1 minus 0.075 to know what the Z is, right? 1 minus 0.075 would give me Z of, the probability for the region over on the other side. Wait, let me rewrite that. Okay, like this one. And this would give me a value of 0.925. I want to know what is the Z for 0.925. Similarly, if I wanted to use the negative one, that would just be much more easier, I think. It would just be 0.075. Sorry, not. This region would be 0.075, and I would want to know what is my negative Z value. Okay, so let's try that. Let's try for the positive one first. I want to find a value, probability 0.925 CDF. What is the Z, corresponding Z? So let's see, 0.925. I have it here, I'm prepared. Don't have to look at module 8. 0.925. 0.925. Okay, so it looks like it's around here, 0.925 over here, and that would be 1.44. 1.44. Remember, when we have our interval, the value of alpha over 2 is your CDF. The value of alpha over 2 is your CDF for your right interval and left interval. So you need to know what is your Z. So your Z is 1.44. Okay, so let's use that. What if we wanted to find for the negative one? Our negative one was 0.075. The value of 0.075. 0.075. It's over here. Okay, 0.075. Oh, whoops. Okay, so you can see that it's minus 1.44. So because they are symmetrical, right? It makes sense. So on right hand side, it's 1.44. On the left hand side, it's minus 1.44. So let's write that in our question. So now we already know what this is. It is, oh, I don't want to erase that. I want to make this smaller because I want to make this solution available to you. Or do I have the solution? I do. Okay, never mind then. So let me erase this. Okay, just now we found out that the value was 1.44, right? So sample mean plus minus 1.44, and this is our sample standard deviation, 0.1 over 10. 1 divided by 10 is 0.001. Why did I use my calculator for that? 0.01. So my sample mean is between times width 1.44. Okay, 0.0144. And I can just substitute this one to be 0.0144. That. Okay, so hopefully I did not make any mistakes. So first step was to find our alpha, find what is alpha over 2. This will be our CDF, okay? And then number 2, find the corresponding Z for our alpha over 2, which is our CDF. So our Z is 1.44, positive, negative, and this is our sample standard deviation. And then you multiply these two values together to get your interval range. Find from table. Okay, so this is your range. So let's see if I did any mistakes or is it correct. It looks correct. You can write it like this, or you can write it in this form as well. So 12.05 plus with 0.0144, that will be your upper limit or your upper confidence limit, is it? And then 12.05 minus with 0.0144, that will be your lower. Okay. So first step, alpha over 2. Second step, find the Z in the table corresponding to the CDF that you already calculated from your alpha over 2. And then third is your interval. You have your interval. I think this makes much more sense than the definitions and all the graphs that we talked about. Please revise, please do more practices. Is there anything else that I want to cover? Well, we have around 5 minutes more. Let me see, another example. Okay. An article, study on the life distribution of micro drills. This is the author. Okay. Reports that in a sample of 50 micro drills, so this is our N. Oh, sorry, before that, does anyone have any questions about the previous example? Was that okay for everyone? Does anyone want me to repeat? So far, okay?
Okay.
Okay. And everyone else, okay?
Okay.
Okay. Okay. Much more convincing. Reports that in a sample of 50 microdrills drilling a low carbon alloy steel, the average lifetime was, this is our sample, 12.68 with a standard deviation of 6.83. So this is our sample standard deviation, 6.83. Find a 95% confidence interval. So we know that 1 minus alpha is 0.95 and alpha is 0.05. Alpha over 2 is 0.025, if my math is correct. Find for the mean lifetime of microdrills under these conditions. This is our first step, we did it. Second step, write our definition for the confidence interval. So mean plus minus Z alpha over 2 and our sample standard deviation of that. So our alpha over 2 is 0.025. This is our confidence interval. Sorry, this is our CDF. So I can pick it from here. This is 0.025, or I can pick it from here. This is minus Z. This is positive Z. This would be 1 minus 0.025. 0.975. They would give me the same value, but just positive, negative for the Z, 0.975. Okay, so I specified my alpha over 2 as 0.025. This is my CDF, or the value outside the confidence interval. Yes, okay. And then I want to know what is my sample standard deviation. I have my sample. Wait, this is not. This is our S, I think. Sorry. S. Okay, so this one is supposed to be S over square root of N. Sorry, my bad. So S is 6.83 divided by square root of 50. So we would get this value as 6.83 divided by square root of 50. So I would get 0.966. Okay, 0.966. So let's go for our table now. We already found this value. Now we want to find out what is this value. And we want to, I'm just going to go for the easy one, 0.025. Let's see. 0.025, oops. 0.025 would be negative Z something. 0.025 would fall here. So it is minus 1.97. 1.97. So 1.97. Oops. So that is 1.97. So your confidence interval is specified by 12.68 plus minus 1.97 times with 0.966. So it's 1.9, quite big compared to the previous one, which was 0.0144, very small range. This one is quite big range. Okay, so I think that is it. No, wait, I have one more thing to tell you. This one. I want to talk about this one, last one, promise. Now we're going to end class. So here, confidence interval precision versus reliability. We saw earlier that sometimes our range is big, sometimes our range is small, right? For a big range, it's not very precise because the values can be between a very big range. So it can be anything. Whereas if you have a smaller interval, you know that the values are just between like, you know, like very minimal values that is plausible for your data. So which is more important? Is it the precision, which is a smaller interval, or is it the reliability, which is the confidence interval? So the confidence interval is actually like inversely proportional. How do I say this? It's like the opposite of precision. So the bigger your confidence interval, the less precise is your values, right? Because it's bigger. So let's see these examples here. For A, 100 of 68% confidence intervals for a population mean. So this is your, let's see this. This is, imagine that you had your distribution, so normal distribution. You had your X over here. Remember that we had the horizontal bar for the confidence interval for the mean. This is what it is. And the straight line is your mu. Does it cover the mu? Does it not cover the mu? So here, if it overlaps the straight line, it covers the mu or the population mean. If it does not overlap that line, therefore, it is outside the confidence interval. Sorry, it is outside the, basically it doesn't overlap. Let's just say that. So 168% confidence interval. So you can see that it's fairly short, it's 68%. Each computed from different sample, although precise. These are all different samples. So first sample overlaps the mean. Second sample overlaps. Third sample overlaps. Fourth sample does not overlap with the mean. It happens. So although precise, because it's fairly short, right? They fail to cover the population mean 32% of the time. This high failure rate makes 68% confidence interval unacceptable for practical purposes. Okay. So most of the time, if you say that your data is like 50% confidence interval, I say that your data is like wonky. I don't like your data. So you have to sample more, or you have to like get more data and get a new confidence interval. So B, 195% confidence interval. So you can see that this one is bigger than the 68, 95%. It's bigger range, right? Computed from these samples, this represents a good compromise between reliability and precision. Yes, you compromise your precision, but you know it's reliable. The value that you get is reliable. 95% confident of your sample mean value. 199.7 confidence interval, this is like really huge, almost 100%. These intervals fail to cover the population mean only 3 times in 1,000 samples that you have. But this is just 100. So if you were to sample 1,000 times, only 3 times, it doesn't cover the population mean. Extremely reliable, but very imprecise. It basically covers like almost the entire distribution. So basically you're just, let's just say 100%. It's almost like that, right? It is very reliable. Your value will always cover the mean, but it's imprecise. So 95% is like the good one. Okay, so that's it for today. We're going to continue. For your exam, confidence interval will be covered. So final yes. Okay, so take care everyone. Have a great rest of the day. The heavy topic, but it happens to the best of us. Take care. Bye-bye.
Thank you, Doctor.
Okay.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Bye. Welcome.
Thank you, Doctor.
Welcome.